almost till the 5 o'clock, and then so I would really request the student, sort of, there was one question from Hirok Kule, I think. I don't know if Hirok, you are satisfied with the discussion we had yesterday. If you want, we can discuss that point, or otherwise, if other have any comment. I mean, I see there's several of you there, so why don't we take at least 5-10 minutes to understand each other, like if there are any questions, comment you have, any of you. So Rakesh Naik, Abhi Modak, just reading the name, Rutuparna and Girija. I think Rutuparna and Girija, they attended the IIT Indore Wala lecture, so maybe they already. Okay, you did. Swapnesh, Bhagyarathi, definitely you are new, Bhagyarathi, I understand. I mean, we talked earlier. Suraj, Ravindra, Dusmant, Suman, I think I know you.
Hello, sir.
Hello, Suman. Sital, Kiti, Swati, yeah. So, I mean, Anuj, Shweta, Navneet, Rupmoy, Samir, and some other. Sorry, so please, do you have anything you want to discuss? Did I go at two? Yeah.
Hello, sir.
Yes.
Sir, I have a small question. Sir, how do you determine physically that low bias lead to higher variance? So how do you interpret?
How did I know that the
Yes.
low bias will lead to high variance?
Yes, sir.
Yeah. So that is just like see, what is the variance and bias? See, as an experimental physicist, so there are few things. I mean, I'm just generally telling in statistics. There are very first thing you should be aware of is sensitivity, resolution, bias in the measurement. Resolution is mostly, sometimes also we call it RMS. If you have a distribution and sort of your detector resolution has got finite stuff. It's not infinite. But what variance is in this context of machine learning is that if you're sensitive, if you're highly sensitive to the data size, which you should not be. Now, what we saw that, if you remember that, I mean, I will come to that. So there are two plot, right? So the bias decreasing, and you start with low variance, and then the variance increasing as you. So, if you, maybe I should show that slide. Showing the slide will make it easier.
Sir, yes, sir, I remember that slide. You can go ahead.
Right. So the point is what we call overfitting. You want to get into, so you want your model to be as close as it can get into the, to describe the data. Like not a single point I want to leave it aside, and when you do that, obviously, because bias is defined as your data minus the model, basically the square of that, naively speaking, right? That's all fine, but then you get into the trouble that that you did in one set of data, and you did it over really, sort of overtrain yourself in that data, and now you get into another data, which is even a testing data, which could be a larger data sample, like in Alice, you have data taking the heavy ion collision data taken over the year. So you did the analysis on some year data, and you want to repeat it, with similar setting for the next year data, but you will see you get into trouble. that because your model is highly overtrained, highly biased, or you can say skewed in favor of that particular data sample, and now you go to another data, your model will not work, which is, or even someone else make a slight modification to your let's say input variable, or slight change here and there, that will give rise to big variance. So the bias will, so that's the problem. So that's not a viable or robust solution for your for your thing. So that is what we call it overfitting. That it's kind of, they go in a opposite direction, and we want to achieve something which is in the middle. If I want to give a, so don't take it like a exact. So if you, when you start to analyze the data and you do this so-called COT optimization, for example, you are not doing machine learning method. You have a series of selection criteria. You are optimizing on that. So we do this S over square root of, some optimization you do, and then you have efficiency and purity. But you see, as you apply the COT, your efficiency will go down. Maybe you cut down more and more background. That is good. You improve purity, but efficiency will go down. So there is a kind of efficiency and purity, they go in opposite direction. Okay, but then where you make it when you call this is my, so you have pretty good efficiency and pretty good purity. So in this case, in your machine learning technique, you want to get to a situation where bias is acceptable, so also the variance. So don't get into the thing that bias ko zero karna hai and variance. So when you get into the problem, or converse also. Okay, Bhagirathi?
Yes, sir. Thank you.
Okay. Anyone else want to bring up anything? Or if you think that was I too technical in terms of did you get some anyway, today it will be much more in a language without much of mathematics. So maybe you will have more fruitful discussion. So let's see. Okay, since people are a little bit, I think probably shy, or so let us
Hello, sir.
Yes,
Hello?
Dukhishyam.
Yeah. Sir, my question is where we can use the negative likelihood method, and we know the binary efficiency which measuring detector. We normally use the binomial efficiency assumption is the binomial efficiency.
Correct.
But when we can apply for this for the physical, where the process in which we think about that, here we can apply the negative likelihood method to understanding this process.
Okay, that's a very good question. So I got your question. So let me try to say, and then you can tell me if I got the question. So your question is, you have a series of let's say input, or what we call feature variable, and you want to sort of see at what stage the multidimensional fitting, multidimensional or this machine learning method. When you will use maximum likelihood method, when you will use neural network, when you will use Brewster decision tree or something. Is that the question, or is it like I don't know if I got that.
Yes, my question is similarly, like we have the outputs. Like if I know this is binary outputs, then we decide, I can use the binary efficiency method or whatever the method which is applicable for me. But what are the outcomes where we can looking, then I decide, this is the negative likelihood method should we apply here.
Yeah, so we mostly look at, so depend which method you want to use, because the same problem can be solved in number of ways. Okay, the same problem can be solved in a number of ways, and particularly if you are okay. So can you just wait for a second? I will, okay, I had to change my sitting place. Just a second. Can you hear me?
Yes.
Right. So what I was saying that the same problem can be solved in a number of ways. Number of method you can use, whether it is multivariate method. I'm sorry, likelihood method or neural network or boosted decision tree method. Now, if you're thinking of classification, I see the point you are saying binary classification. If it is a classification or something like you are doing, let's say charge hadron identification or what we call PID, right? So let's say you have two hypotheses you want to kind of, proton versus pion or pion versus kaon or something like that. That's the problem you have in hand. Now question is, when I go to this method versus that method, let's say maximum,
Right.
when I can go to maximum likelihood method, when I go to neural network. So this will depend on the feature variable. So one of the things you have in mind that the feature variable will have a decisive role in determining, sort of which method will give you the best possible
Sir, in the
performance.
feature variable means like
The
I will
input.
check the efficiency, purity of
Yeah,
each.
exactly. That is what I'm talking. So in terms, so let's say you have same set of feature variable, right? So your detector, Alice detector, you have same set of feature variable. You take that feature variable. Now you get to the, so it's like one thing is fixed. Now you get into the method, like which method to be used. So likelihood method in quite evidently, like it works fine. I mean, no issue. But then you see that some of the feature variable are highly correlated, and correlation of nonlinear nature is difficult for likelihood to, to handle that. It is really difficult, and that is where getting into nonlinear method, machine learning method, namely neural network and BDT, that makes your life so evidently. So what are these feature variables? These are the that are some kind of detector level, higher level object, higher level information coming from your detector. Okay, let's say it is d by dx. If you have a TPC kind of detector, and that is 1 by beta square Bethe-Bloch formula or log beta in the high momentum side, or you might have time of flight, or you might have, I'm talking in the context of PID. Or you might have a Cherenkov detector where when the velocity goes higher than the threshold, in certain velocity, then you get the Cherenkov radiation, right? So those information, when they come, they obviously they have their own applicability. Someone is applicable for some momentum, some is not applicable for other. But more importantly, across the variable, there may be some correlation. And if it is sort of linear correlation or something like where you can easily model the correlation, then in your likelihood, uh, you can take care of that. And but if you have a very complex correlation, particularly nonlinear side, likelihood is not able to handle it. Then you have to turn back on neural network particularly, and okay, there is certain issue between neural network versus BDT. So actually, so I will recommend at the end there is a kind of so-called TMVA, this toolkit for multivariate analysis. Most of us use that, which is now integrated with root framework, right? So if you look at the TMVA manual, there is one page at the end, I guess, end or beginning, which is basically address your question that when you are a user, you are a kind of informed user, and you want to make a decision which way I should take. Okay, I mean, this is the problem I have in hand. Should I use this? Should I use that? Or, so you decide the feature variable, and then in each of the method, you check this ROC. So that is the part I was saying at the end.
Thank you.
You have to look at the ROC integral to decide. The ideal situation is the ROC integral being 1, and I can give you in writing, you will never get it to 1. So how close you can get in the ROC integral?
Thank you, sir. Yes,
Okay. Yeah, I think anyone else? Otherwise, we get to. Okay, let me start there. Okay, I think we were here. So all right. So since Dukhi-san made this point, this is exactly the point we wanted to discuss, that when you know or when you can make a decision that which way I should go, should I use the classic, I mean, why would I go to a machine learning method? I mean, some of you might think, why the hell I worry about this machine learning method? I should just go with classic cut and count analysis, which is obviously fine. You can use it. It is everything transparent. The last few, whatever 2 lecture we discussed, basically I wanted to kind of tell you that machine learning is not really like a black box. You can, if you put a little bit of effort, or if you try to sort of get the basic concept that we discussed, you can understand what is going on under this machine learning, which is basically a multidimensional optimization, basically. And now, how do this optimization happens? But then, yes, that's all fine. But then, how do I quantify in terms of that whether I should go for that or not, right? That's a question that Dukhi-san posed. And the way we call it, you look at this classifier performance, what we also call it ROC curve, or receiver operating characteristic, ROC curve. So here, what you see that in the, let's say in this plot here, or let's discuss this plot. This is from Atlas simulation. So this is a so PP collision, PP collided, and you get either a Z boson or a virtual photon going to tau plus tau minus, very easy, and then tau decays to either hadronically or leptonically, and now tau, there you have various decay channel of the tau. So unlike an electron or muon where you have a clear-cut signature, so tau you have to identify depending on the final state. And particularly if you have neutral particle, particularly pi 0 that decays to 2 photon, that kind of final state is not so easy to distinguish. Although there is a good calorimeter, electromagnetic calorimeter Atlas has, so also CMS. So what they have done is basically they used a kind of machine learning technique, actually a boosted decision tree. And in this technique, they try to reconstruct different decay mode. And what you see in this plot, that at the generation level, at the Monte Carlo level, at the generation level, what is that decay, okay? And then you want to see that what fraction of the decay for the particular decay you are reconstructing it as like that, let's say tau going to a charged hadron plus a neutrino, right? Tau plus going to, let's say, pi plus nu tau. What fraction of the time it is reconstructed as the same? So if you have idealistic world, you expect this diagonal matrix to be all 100%, and this off diagonal element, which we call confusion term, okay, you have generated something, but it's reconstructed as something else. Okay, so that confusion term, cross term, in an ideal world, that should be all 0. Okay, and you can see from this table, this is best what let's say Atlas has achieved. So for the probably the best one you get when you have 3 hadron, that is you get close to 93%. Okay, followed by this single hadron where you get to close to 90%. And the worst performance you see as you have more number of pi 0, and that's no prize in guessing that this neutral particle are quite notorious in reconstructing them, particularly in a hadron environment such as LSC. Okay, that is one thing you see. And in the second plot, you see this rock curve. So here the job is to distinguish. So you have jets, and all of you know jet, hadronic jet. I understand you had a lecture in standard model, and I'm sure during this lecture or even otherwise you know about jet. So these jets are basically bunch of particles coming out, coming due to the hadronization of the so-called color object, color particle, namely quarks and the gluons. Now, given the properties of the quark and gluon, that factor percolates to the kind of the jets that come out of that. Basically, in gluon, you always get the quark splitting QQ bar, and then, but in quark case, it is more like a Bremsstrahlung, right? Quark, Bremsstrahlung, gluon. So there are certain feature difference between the jets initiated by quark versus gluon. So those kind of feature have been implemented into a multivariate method. In this case, NN stands for neural network. And then you see different kind of in this particular thing, what you see, the signal efficiency versus the background efficiency. And for an ideal world, you want to have 100% signal efficiency, 0% background efficiency. You can see my hand where I am showing. This is where you want to target to. And then you see this dashed line is kind of, if you are below this dashed line, you are definitely, you're not doing a job well. So this is worse. And higher up is better, but then how better? The best is here, and that is never achievable. That's like the way I said here, getting 100% 100% matching between generation and reconstruction decay mode is never going to happen. So here, what you see in different kind of implementation of your neural network, like for example, even the feature variable that you have, you see that your this area under the rock curve, so that you see that says area under the rock curve. So for real ideal case, it should be 1, right? But you see that sometimes it is less, and how things are improved. And this is, in this particular case, is the best what is achieved. Okay, so that is, yeah.
Sir, I have a question.
Yes, Swapnes, is that Swapnes?
Yes, sir.
Okay.
So this is regarding this true positive ROC curve, actually. So we have two curves for weakly supervised NN and fully supervised NN.
Hmm.
Okay, and they are kind of overlapping
Hmm.
completely. So
Right.
I don't want to make this understanding that the supervision, I mean, it seems that it is redundant or what, something like that. Okay, since weekly supervision and fully supervision both are giving the same results.
Right.
Yeah,
Right.
so
Right. Right.
can you
So
please comment?
yeah, yeah, sure. So yeah, no, it's good comment. Good question. So yes, other thing I should say, um, quite often you will be getting that it is not a unique. I mean, so you may get similar performance or exactly same performance in two different cases. Okay, so it's not ruled out, absolutely ruled out that only one method will give the. So in this case, what you see the overlapping between the blue curve versus, so the question from Sopnes is that if I have, I mean, if I understand this question, so you have this blue and green on top of each other, each of the area is 0.89, then which one to pick up, or why they are like this? Well, this is an interplay. This is an interplay between the feature variable, um, and so you have to pick up the one. Now, question is, you'll say that which one to pick up, right? Let's say, should I take weekly supervised or fully supervised? These are the things you will have to see in overall. Like there are different uncertainty. Let's say if you think that actually you can pick up any of them, but then if you say that can you be little more quantitative in terms of so what I will go to the second stage, I will see that what are the lacuna, what are the between the two method, which one is more robust. Okay, they give same performance for sure, but which method is more robust in terms of systematics, in terms of because anything you apply, you have to also depending on how you finally get into your data when you go to your data analysis. This is mostly done at the Monte Carlo level, right? Your training and testing is done at the Monte Carlo level, and then you get into the data. When you get into the data, there will be some systematic also. So in deciding finally which method to pick up, you have to look at the robust, the comparison of robustness between the method, as well as the what are the systematic you have to deal with. Yeah, but you can pick up both of them are equally good as far as here the area under ROC curve concerned. So both of them should be fine, but then you have to make a choice, and the choice has to be based on some further solid grounding. Did I answer you, Swapnesh, or did I not get your question properly?
Yes, sir, yes, sir. Thank you. Thank you.
Okay, so that was about when you have binary class, but then obviously when you go to the multi-class classification. So initially we said blue versus red. Now you add another here, like golden color. And now how do we do about it? In a classical cut and count analysis, the decision boundary will be like either you put this or this, and but then when you go to the machine learning method, your decision boundary will be more complex. Okay, and in this case, you will be able to use the same neural network or the same boosted decision tree machine learning method. Now, what you have in the binary case, your target is 0 or 1, right? I mean, some signals should pick around 0 and background. So in this case, what you will be getting, you have n number of input parameter, okay, n number of input parameter. Now, you will get depending on, so let's say, let's put this way. Let's say I want to distinguish between the, so B tagging, I suppose all of you know B tagging, like you have jets inside your, hadronic jet you detect, whether that jet is initiated by a heavy flavor quark, namely a B quark or a C quark. Okay, I suppose I think in Alice, most of you are working in Alice. I guess you have heavy flavor tagging, right? B tagging or not. Anyone want to make a comment? Whether in Alice do you use the B tagging?
Sir, I had this bit again some paper, but I don't have experience. The heavy flavor people use this.
Yeah, it is heavy flavor,
Yes,
right?
but
Okay.
I don't know.
Okay, so I can very briefly tell you. So, so these jets are initiated by, as you discussed, by quarks and gluons. So out of the 6 quark, the top quark doesn't hadronize because it's too heavy. So it decays before it can hadronize. The other 5 quark, namely UD, CS, and B, they hadronize. In the case of, because this hadronization is a strong interaction process, so if you have a jet initiated by a B quark, as process of the hadronization, there will be evidently, since you start with a initial state which has a bottom quantum number plus or minus 1, depending on whether it's a B quark or anti-B quark, B anti-quark. So in the final state, you should have a B meson or a B hadron, B meson or B baryon. So there will be net, if you start with B initial state, the quantum number must conserve because it's a strong interaction process. Now, once you have the B meson, they decay. And the decay is mostly weak interaction process. And weak interaction, as you all know, it maximally violates most of the symmetry. So this, what we are saying, the bottom quantum number is not a good symmetry for a weak interaction. So in any case, that this B meson flies certain distance before decaying. So inside your jet, you will see a secondary vortex, right? They are not coming from the primary interaction point or primary vortex. They fly certain distance before decaying. So that's a telltale signal for so-called the B jet. And in CMS and Atlas, it is very heavily used. And in LSCB experiment is also used in a different context for the CP biological measurement. So you have a B jet, then you have something similar like a C jet. I'm sure all of you have, or pretty much you've been knowing about D meson and all this, more like a charm hadron. So you can get a charm meson and charm baryon. Now these guys are also, they decay. On an average, the lifetime of a charm meson is smaller than a B meson. So their secondary vortex is somewhat closer to the primary vortex compared to the B meson case or B jet case. And if you compare the other 3 quark, namely UDS, they're all kind of prompt, so you don't see any signature of secondary vortex if you have a jet initiated by U quark, B quark, or S quark. Anyway, so now you see 3 classes of event: UDS in one box, charm quark in another box, charm quark jet, and B quark. And this is a multi-class classification. So I have already said that secondary vortex, the signature of the secondary vortex. And so if you have a very high precision pixel and silicon based tracking detector, those information are used. The impact parameter, there was a question by raised in the very first lecture, impact parameter part that comes into your rescue. And we put those information and then we look at the output. So it will be like one output for B, C, and for rest. If you want to do the discrimination B to rest, so it is like the output of what B like over the sum total of all. Okay, and this is C like sum total of all. But if you want to the B versus C, so it is like the B like output divided by B plus C. Are you getting me? So it's depending on, in the case of 2 digital classification, binary classification is simple. You just have 0, 1. But in the case of multi-class classification, you have more than 2. And then you have to get into this different output. And accordingly, depending on what versus what, or you want to look at the global, let's say, probability of one kind of class of event. So it will be like the output for that event divided by the sum total of, or sum total for the all event. Okay, so so I think the main message of these 2 lecture, 2 and little more than we haven't finished today's lecture. I try to tell you that what is the underlying principle, the statistical technique, the mathematical technique underlying the machine learning. It is basically, okay, we'll also talk a little bit more. And there is a question I have not forgotten, that how much data is required. So it will be next. So yeah, so the idea is you use these techniques, and data is your, like, you know, you take from the data, like use this technique, and let your computer learn from the data, and then make prediction, like for other data set. So it can be supervised learning, where you know inside the data what is the label, what you are expecting here, what you are expecting here, and not. So supervised or unsupervised, you just give the raw data and let the machine learning to make some kind of what we call see some structure, and try to get around it, so-called clustering part. Okay, so now I will change the gear and get to the case where we'll talk about I mean, this time it will be more like not into too much of mathematics, more like if you want to use TMVA or multivariate technique, then sort of how to use that, and then this question of how much data required. So those are the things we'll talk about. And right, so so normally, like in the data analysis, like when you say particularly in the classification case, so we have the total data sample, and the total data sample is supposed to be union of many interesting classes of event. In this particular case, for example, you see the data is part of, like, there is sample A and sample B. There's 2 classes of event. And okay, there will be certain case that it is difficult for you to distinguish between the 2. And obviously, in ideal world, you would like to have A, B completely non-overlapping, but in real world, it never happens like that. Any times you have a distribution, what you might be doing for your thesis, PhD thesis, what you call signal, you will not get 100% pure signal from the raw distribution. Of course, you can do a background subtraction and something like that, and but just from the raw data, from the raw analysis, there is no way you can get entirely pure signal. Okay, and so basically, what you want to determine that given a data, like the total data event you have, and event by event, you don't have like this event is entirely signal or this event is entirely background. For each event, you have either signalness or backgroundness. Okay, A-ness and B-ness, and that's kind of expressed in terms of probability. And so it's like see this distribution that you see here. There are 2 feature variable here. Let's call it Y and X here. And in these 2 feature variable, you have these 2 classes of event, A and B. Now, if you project that into the either feature variable y axis or x axis, you see this distribution looks fairly close to a Gaussian distribution. Okay, and in a cut and count analysis, you will be like depending on which one you want to select or which one you want to reject, because the definition of signal and background, that is also not unique. Like your signal could be background to your friend's to your friend, and vice versa. So therefore, depending on what you want to do, you apply a cut on one variable, go into second variable, but the idea is every time you apply cut, there will be some efficiency loss involved, and you want to get the best possible classification scheme by taking the information from both these input variable. So instead of putting the cut in two variables independently, you want to deal with one output variable which optimally combines the distinction power of the two independent variable, two variable, and that gives you better sensitivity. At the end of the day, when you make a measurement, depending on whatever measurement you are doing, you want to improve, you want to enhance the sensitivity. And so therefore, this machine learning technique is very important results for many of the analysis, and especially you have a very complex data set such as offered by the LSC. Okay, so yeah, so the one thing I want to tell you, and probably I said in the first slide, so there is like the way there is no unique definition of signal background. It all depends on what you are doing. Similarly, there is no unique definition that this kind of method will work for everyone, right? So it all depends on the problem you have in hand, okay? And you want to make a judicious decision that what is the best choice. And that judicious decision will have to based on certain, like, you know, we are all physicists, and science all, you know, particularly physics, all based on measurement. You know, it's all quantification, or, you know, whatever, why I said this is best compared to that, why that is, you know, so that has to be, that is where it comes into this ROC or things like that, right? So just blindly do not use something just it sounds fancy, machine learning sounds fancy, so okay, for my analysis I use machine learning. That's not the right thing to do. Okay, so you have to make a really judicious choice. And so let's see. Right. So I don't think I want to get you through this cut and count analysis. That's what you usually do. But basically, we try to optimize on. Can you see my slide in reasonable shape, or you want me to make it full screen?
Yes, sir, it is visible.
Okay. So yeah, so in cut and count analysis, you essentially do some kind of optimization that where to apply the selection criteria for doing the analysis, and that decision, again, as I said, everything is based on logic. You know, science, everything is based on. I mean, I shouldn't bring religion here, and science and religion. That is the key thing. That science is based on certain thing. So here, for example, in cut and count analysis, this so-called significance is what is a measure of the sensitivity, and that we want to optimize on. And there is one very simple linear method. It is called linear discriminant. It goes by Fisher, the person who introduced this concept. So what it means, you have n number of feature variable, and you combine, instead of independently cutting on each of them, you combine them in certain way, and that's this alpha is kind of, see, this is a linear way of combining that. And the beta is some kind of, let's say, offset, okay? You can all, I mean, it doesn't play much role eventually. So we can drop that. So basically, when you combine your n number of feature variable, and then the other one is the n number of feature variable, other one I stands for the data event. So ith event. So when you want to do that, so this alpha I is what you want to optimize on, right? So just adding 5 into x1 plus, so x1 is an input variable, 5 into x1 plus 25 into x2. You don't know whether this 5 and 25 are the right choice or not. So there is a way to determine this coefficient alpha. It's a vector actually. And the way you do, we discuss about in the where there's a question that variance, bias and variance. So here we define what you want, so-called the mean and the sigma, mean and the sigma of the final output distribution. So think of now you see, you look at this. You look at this distribution in this x-axis, and so this is x-axis and y-axis. You see, they look like Gaussian, but they're separated. They are not one top of each other. If they would have been exactly one top of each other, that input variable or feature variable is not a good variable for your case, right? So what you see, they are Gaussian-like. Their means are quite different. And also their sigma is also quite different, okay? Now, when you want to go to the effective, that feature, like you want to combine these two guys, let's call it alpha 1 x plus alpha 2 y. Now I want to optimize this value of what is the value of alpha I should take. So that optimization is done by defining, to find out so-called the Fisher mean and the sigma. So the way you will be doing is, so let's say it's a sort of binary case I am taking. So you have a signal and the background distribution, and there are, let's say, several number of variable you have. And so that alpha into, so if you have two distribution, so you want to separate the signal and background as, so they should be as well separated as they should be. So there you get the difference of the mean, okay, difference of the mean, and then so that is why your numerator. So this one, so this J alpha is what we want to optimize on. We want to maximize this. Now, effectively, there are two things. One is that you want the effective mean between the Fisher, the final Fisher output distribution that you should get. They should be as large as possible. And the second thing you want to do, that the so-called the variance should be as small as it should be, like that effective Gaussian, if both of them become two Dirac delta, that is as best as that can be, right? But obviously you will not find the Dirac delta distribution of two Dirac delta. There will be Gaussian, more like Gaussian or sort of like that, and there will be overlap. So you want to minimize the overlap between the signal and background, and the way you do that, the mean should be as far away as they possibly could be, and also the variance for each of the things should be as tiny, as narrow as they should be. And so basically at the end of the day, it's an optimization problem, right? Everything we do is mathematical optimization, whether it is Fisher discriminant method, likelihood, or neural network, or boosted decision. These are the methods largely we use. In LSC experiment these days, more and more, I think, particularly for CMS and Atlas, people are mostly using neural network and boosted decision tree. Okay, and now they're going into the deep neural network. So yeah, so you see that once you define this J, which is a function of alpha, because each of these term there is that new, like the way we have defined here in these two equations, you see that how alphas are being presented. And once you have that, the whole idea is you want to optimize on the alpha value, because input parameter you cannot do. I mean, that is detector given, almost like you cannot tamper with that. Whatever your detector gives, it gives. I mean, that is what given. But you want to get the best out of that, right? Given that thing, how best I can get my experimental sensitivity. And that's what you do by optimizing on these alphas. Okay. And so I'm not getting into like the nitty-gritty detail of what is very written. I will just sort of glancing you through. So you see this, there are this, what you saw in the maybe 2-3 slides before, the two cases, like you have two Gaussian-like distribution, one and another Gaussian-like distribution. Now, individually, you could have applied code here, but now you see, you go here, right? And now you see the net overlapping, so it has reduced, right? Well, I think you have to really integrate it out and then see. Yes, so the Fisher discriminant method that works reasonably okay. I will say if Fisher is quite a linear method and it works fine, then why the hell I get into more complex method? So your rough target should be that I should go for a simple method. That is the first thing. And then in the simple method, what do I get? And then can I make it a little more complicated? And then if I do make it complicated, how much gain I'm getting? You know, there's a kind of cost benefit, right? In business model, there's always called cost benefit. In physicist way of it is called, sort of, do I gain anything, or just because sir told me to do this thing, should I do it? No, you shouldn't do it. You go step by step and see that what you gain in terms of sensitivity, that going into more complex method.
Hello,
Okay.
sir.
Yes.
My question in the previous slide. You show the one more. Yes. Here there's a
Here, sorry, yeah.
this here in the three cases, you say the far away from the mean. We first look the mean of the signal and background should be far away. And what about the width? We also take care
width
of the
should be, yeah.
narrowed.
So if you look at this expression, just look at this J alpha. So you want to maximize J alpha with respect to alpha. So maximum means your numerator of your ratio should be as large as possible, right? Okay. And the denominator should be exactly as small as possible.
Okay. Thank you.
Yeah, but you know that these are the thing like ideal versus real. I mean, you have to be satisfied of what best you get. I mean, I would have wanted this blue to be a Dirac delta here and red to be Dirac delta here. That way you have 100%, like you apply code here, then you have entirely red, you are rejecting entirely the blue. So efficiency 100%, purity 100%. Not possible. Your ROC integral 1, not possible. So you have to sort of compromise, or you have to stay with this much of so-called the background contamination in your sample. Okay, so now let's get into the neural network. So one of the quick thing I want to say, that you'll say, well, if neural network works fine, then why do we go into more complicated stuff? So the problem is, you can see if I have expression like this, okay, that sum of your total output is sum of alpha I, that's what I showed here in more this time. So you see that if x1 and that any of the 2x, if they are correlated, the correlation is of linear type. That means x2 I can express as mx plus something, right? That's your first thing you do. In that case, effectively you can reduce your Fisher discriminant complexity or dimension by 1, right? Because I can replace x2 by mx1 plus c, and there is an x1. So x1, that 1 plus m, right? So it is like you start with n dimension. If there are two feature variable are linearly correlated, you can crop them into one effectively. So you reduce that, but that's fine. That is okay for Fisher. But if they are not linearly correlated, Fisher will not work. Okay, it will give you crap. And that is where neural network helps. So neural network is basically motivated by what is there inside our brain, the way our neuron system, the way one mosquito biting you here, like you might be doing something, but without a second thought, your hand exactly get into this place, right, where the mosquito bite you. I'm sure all of you would have this experience, mosquito or something like that. So you know, so that's happens. You have the neurons all over the place, and there is a central processing unit somewhere sitting inside. Okay, and this message getting into from one place to another, and then the central processing unit say, okay, now instruct to this and take care. Right. So that is what happens roughly in the neural network method in the analysis that we do in high energy physics. So you have information coming in from several feature variables. Those are kind of, in a sense, neuron. But then we want to now interconnect these neurons. Okay. And the way the interconnect is done is what we call the there is a yes. So the way it works, so there is sort of these are what is in this side. These are your detect. I mean, what you get from your instrument. Now, this is what you are designing. Okay, this is, in a sense, you are bringing in that connectedness. You see that every place like X1, there is you have hidden layer, and in the hidden layer you have sort of connection from each of the node. So this is like input layer, let's call it. This is hidden layer. I mean, it's obviously there is. If you add more and more hidden layer, you will add more and more complexity. And obviously, whether you need that or not, these are an optimization problem. These are the something you want to test it out. That is my problem complex enough that warrants higher level hidden layer, more number of hidden layer or not, will be decided by the complexity of your problem in hand. And so what you can see that these input layers are all connected. And through this connection, which seems like pretty easy, you are essentially imitating, you are essentially trying to capture the nonlinear correlation among these input variables. If they would have been only linearly correlated, as we said, you really don't want to get into here, you are happy with the Fisher method. Okay, so that's the rough idea. So in that case, you showed output equal to sum upon ij or whatever alpha ij xj. There was some beta term you put as an offset. Here you are is a kind of weight vector, and depending on the weight, depending on like which connection. So each of the connection. In the Fisher case, you optimize on the alpha value. In this case, this connection that is what you will optimize. So this connection between from, let's say, X1 to this, sort of to different layer, and then X2 to this. So each of the link that you see, each of them come with a W, let's call it, this is X1. So this connection is W11, this connection is W12. So first subscript tells, let's say, from where it started. Second subscript tells you where it ended. So you have those many connections. Each of the connection is a parameter to optimize on. Okay, and yes, And this beta is like the way in Fisher also you have some kind of offset or bias that is been added. Yeah, and so how we express that, basically we use so-called this multi-layer perceptron method. So you combine several layer of perceptron and in a way so that you get a refined separation between two classes. Obviously this we say in the binary case, but you can obviously, so let's get here. So in this case, if you have binary classification, your output will be only one, right? Because in that case you have 0 and 1, but but if you have, let's say, multiple classification, like the way we said BZ, CZ versus the light flavor jet, namely jet initiated by U quark, D quark, and S quark. So you can have 3 outputs. No, I'm sorry, it will be 2 outputs. It is 1 less than that. Okay, so I'm sorry, you'll have 3 output, but then depending on what versus what you want to do, out of these 3 output, you will kind of do B versus C or B versus the rest, okay, or C versus the rest. So yeah. So so we use this so-called sigmoid function. So let's see that. So I have half an hour more. Maybe I just
Yes, sir. In the timetable they sent to us, it is your time up to 5:30.
okay, fine. All right. So
Sir, I have
yeah.
just one comment. In neural network, you say we each connection point we find a weightage number. Then there should be starting point, there should be ending point. Then how we decide the end point? Where should be end?
No, I mean, what I mean by endpoint, so I mean, what I mean, so this is the input variable, and this is like the node, the connection between the node. So I'm just saying that weight file, we express it in terms of yij, sorry, wij, while I is saying indicating from sort of the here to here, right? So if you have another layer, so it will be from here to, I mean, you don't go directly from here from the first layer to the let's say second hidden layer. So you go, connection goes from layer number 1 to the next layer. If you add additional hidden layer, then from that first hidden layer, the connection will go to the second hidden layer, and so on and so forth. So when you say deep neural network, what do we mean? We add and more hidden layer. So the idea is
if we add this process like one node, then another node, it is going on. Then when we should stop? How decide
right,
to stop?
right. There? So the question you are asking that how many hidden layer I should have, and yes, inside the hidden layer, how many node I should have. So these are kind of parameter is part of your optimization. Like, so you want to achieve. So what you want to achieve, like that, the end result is a binary classification. You want to achieve the best possible separation, right? So you want to so when you want to optimize on this some on let's say
W.
Yeah. So you want to optimize on the W. Okay. Now you want to see that if I go from one hidden layer and add another hidden layer, I see in terms of the ROC, in terms of at the end of the day, quantification will be done like your whatever sort of you have two classes of event, and I want to separate them in optimal manner as much as possible. Now, where do I stop? Do I bring in more and more hidden layer, or I stop in one hidden layer? If I can get with one hidden layer with a less complex situation, you are getting, right?
Yes.
Now, adding more hidden layer, is it really helping me in terms of ROC? That is what we have to see. So that when you do the training, you have this parameter as part of your train. I mean, you can, so you start with some input value, and if you want to change it, you can change it and then see your performance.
So if you add more parameter, it should be better.
That's not necessarily true. I
Okay.
mean, sometimes
need
even
to be checked.
it can crossfire. I mean,
What are the variables? Okay.
yeah, I mean, the thing is, see, if I add more complexity, let's say your ROC integral is 0.97, let's say. In the other case, you get 0.971. So you add more complexity, which will add into your simulation time and your processing time. Now, question is, you know that any measurement you do, there will be uncertainty. There will be statistical systematic uncertainty.
Right.
Now, is this 0.001 improvement, is it worthwhile of the pain of getting into this thing? While you know your eventual systematic will be larger than that, answer is no.
Okay, thank you.
So, so this sigmoid function is what we call the activation function that we use. There are several activation functions. Sigmoid is one of them, which is given by this plot here on the left, and in the right you see the expression. And there is also tan hyperbolic wedge, and there is a step function which is 0, 1. And there is also a radial function. Largely speaking, we use sigmoid function. So here again, that this is also a optimization parameter, that whether I should go for sigmoid versus. So if you use exactly same input variable, same structure, now I want to change the activation function. Do I get anything going from sigmoid to tan hyperbolic? Largely, it is found out that sigmoid probably does the best, but yeah. I mean, not much of difference compared to other. So default option is sigmoid, but if you wish, you can always try to see that for your problem, whether you get any improvement, any appreciable improvement, not any improvement, any appreciable improvement in terms of your ROC integral. Okay, so one thing, so I'm not getting into all the nitty-gritty detail, but we'll come to that. Let me just tell you the key concept, and this slide I will make it available. So, so where do you start? How do you start? So you remember, now you see the mathematical part. Right now, I'm not talking of any mathematics. The mathematics part was discussed earlier. So the point is, so we talk of the loss function, right? We talked of the loss function. We talked of the loss function having contribution from the bias, variance, and you know. So yeah, so so here when you do this weight, you have a set of weight. You make some guess. Okay, you make some guess of this weight, some starting point, and with that you find out what is the error in your out classification. If it's a binary case, you want to select one versus the other, and that error you want to keep minimum. So you start with a set of weight, and then you get into that gradient descent method, what we discussed, that which is basically you slowly change. There is a learning rate, you slowly change, you go to the new set of weight, and with that you see which direction your change of error is going with respect to this change in weight. Is it going in the right direction or not? And then you reevaluate. So this thing is a feed forward system. You feed forward system, it goes on to the level. Does it go ever? No. The stage when you get into the stable, like you don't see any change anymore. So you have essentially reached the global minima. So when the result is stable and good enough, we stop iterating. So that is why you see initially that if you run this TM, yeah, okay. Yeah, is there a question? Swapnesh? Swapnesh, can you mute?
इमीडिएटली ट्रांसफर नहीं हुआ ना पैसा मेरे
Okay, so yeah, so this is what it is. We define the so-called error like the way that you see in this equation. And if you have whole data sample, each of the data sample contain an event, so you can divide, you can calculate the total error, and you want to optimize. So because yi, you see, yi is a function of the weight, right? That coming from the from this expression, that how the input, the feature variable are communicating with the different stages of the network. And yeah, so this is the way we just said that you start with some set of weight and evaluate the error corresponding to that, and then you slowly change and delta by the weight from the initial value, and then you see which direction you are moving. Okay, are you in the right direction? If not, you immediately come back to the initial weight and then further go. Okay, so, and the whole idea is once you reach here, okay, it doesn't matter from that, in whichever direction you go, you'll see the error to be increased. So that is the point you make a decision. I have reached where I wanted to reach. Okay, so this is called gradient descent method. I actually have to go somewhere. And yeah. Right. So yeah, actually I have to go somewhere. So can we? Yeah. I don't know. So what I will do, maybe I will put my video. I'll record my video because I have to go somewhere. This is Saturday. So can we just take at this stage a break? I'm sorry that there is 20 minutes and I could have finished that, but so what I wanted to say, so I will share with you the slide where I will highlight the important thing. This is a question someone had raised, that how much data we need. I think in the first lecture, and yeah, that what is overtraining. These are the thing I wanted to tell you. But what I will do, if you don't mind, I'll stop here and send you the slide, and I will highlight the important point. Yeah, I think that is what I will do. Sorry, and if you have any questions to what we have discussed, that we will take right now. So a bit sorry about it. Okay, so so what I'll do, I will share my slide. I'll put to the Indigo. I will keep only the relevant part of the slide, and maybe what I'll do, I'll send my email address, and then you can read it and send me your comment or question. Okay, over email.
Okay,
That
sir.
is the best I
It will
can
be
do.
better. Okay.
Yeah. So my email address will be available, so you can send me your question.
Okay, sir.
Okay. Thank you all. Thank you.
Okay, thank you, Professor Mohanti.